Stem cell therapy is normally thought of as a way of simply putting in cells whose genetic composition is identical to the rest of the body, but whose health in other ways has been improved or rejuvenated. However, stem cells can certainly be genetically modified outside the body before being introduced into the body, and there may, in many cases, be value in doing that. Some things that people are already looking at, for example, are introducing new blood stem cells into AIDS patients that contain an AIDS-resistant gene, a gene named CCR5. A very small proportion of people naturally have a variant of that gene called delta 32, which confers very strong resistance to HIV. And if you could give that variant of CCR5 to other people, then this could be an extremely powerful therapy. Luckily, the cells that need to have that variant are blood cells, which means that they come from blood stem cells. And so a bone marrow transplant with this appropriately modified version of this gene would be very powerful, and that is already being worked on. There may be very many other cases of inherited diseases especially, which could be modified and indeed perhaps cured by using genetic modification of stem cells for stem cell therapy. Now, in the case of aging, this may also be a good way of delivering certain of the SENS therapies. The one that's most obvious is LysoSense, the lysosomal enhancement idea for getting rid of molecular garbage inside cells, because here we have to introduce new enzymes into these cells, enzymes that are not encoded in the normal human genome. And in some cases, it may make sense to actually introduce the enzymes by injecting the enzymes into the circulation in the same way that we already treat certain inherited diseases of lysosomal function, called lysosomal storage diseases. But in other cases, it may actually be preferable to make genetic modifications of stem cells so that the blood cells or the other cells that are created from those stem cells are able to have the genetic modification and thereby not to accumulate the molecular garbage that we're talking about, and perhaps even to eliminate the molecular garbage that had already accumulated. Some of what we're going to need to do in genetic modification of people so as to implement SENS will not, or at least is almost certain not to be, able to be implemented using ex vivo gene therapy, the genetic modification of cells outside the body that are then introduced into the body. Some of it's going to have to be done by genetically modifying cells in the body itself. And that is what's called somatic gene therapy. The way it's normally done is by engineering a virus to contain the engineered DNA that we're interested in, and not to contain the DNA that the virus naturally has that makes it bad for us. And of course, gene therapy as an idea has been around quite a long time, and in fact the first clinical trials of gene therapy happened about 20 years ago. But it's had a pretty rocky ride because the fact is there's an awful lot of risks involved in gene therapy, and it doesn't really work very well yet. There are certain diseases for which a very low hit rate, in other words, getting a suitable genetic modification of a very small number of cells, is enough to actually cure the disease. But in most cases, you need to hit quite a lot of cells, and we really just don't know how to do that yet. We at SENS Foundation are very interested in helping to address that problem, and there's one particular approach to improving very substantially the ability to safely introduce new DNA into a lot of cells in the body, which we are just starting a project to explore. One of the biggest dangers in somatic gene therapy, and actually it's also a danger for ex vivo gene therapy where you genetically modify stem cells and then you introduce them, is that on occasion the gene may go into the genome, the engineered DNA may go into the genome in the wrong place, into a place that causes damage by virtue of disrupting the DNA that was already there in a way that you don't want. In general, that disruption is harmless, but very occasionally it may not be harmless. It may actually make the cell cancerous. And there have been genuine cases of this in clinical trials for particular gene therapies. So people are very interested in ways to stop that from happening. And the most obvious way to stop it happening is to develop a gene therapy vector, a type of virus, that preferentially goes into a particular harmless place in the genome and does not go into any of the potentially harmful places. Now, it turns out that there are some viruses that naturally do this. There's something called AAV, adeno-associated virus, which preferentially goes into one particular site on chromosome 19. And people have been very interested in that virus for quite a long time for exactly that reason. However, it turns out to be quite complicated to make that really work, and the hit rate is not good enough. It still has random integration at an unacceptably high level. So people will want to find other ways to go about this. And there are lots of really creative technologies now out there that are being explored to do exactly that. I'm very optimistic that quite soon we will have gene therapy that very robustly does not disrupt DNA that it would be dangerous to disrupt. I believe that other types of manipulation of gene expression, other than gene therapy, are also potentially valuable in treatment of aging and, of course, in medicine in general. A lot of interest these days is in RNA interference, which is a method for inhibiting the expression of particular proteins by introducing short RNA molecules that interfere with that process. And that's got a lot of potential. People are looking into it in a variety of different applications. One area that people have been trying to look into it for is cancer, to see if you can close down cells that are overexpressing genes that they shouldn't be overexpressing, for example. Personally, I'm not very optimistic about the application of this for cancer because it's just too easy for cancers to mutate into a form that makes the RNAi ineffective, the short RNA not work anymore. But in other applications it might be useful. So the brain, of course, is arguably the most essential organ of the body to actually repair from the damage of aging. There's not much point in rebuilding the rest of the body if you're demented. How hard is that? In particular, is it significantly harder than the rest of the body? I believe it's not significantly harder than the rest of the body. Ultimately, the brain is certainly vastly more complicated than any other organ, and we are vastly more ignorant about how it works than we are about any other organ. But the thing about SENS, the thing about the whole preventative maintenance approach to combating aging, is that we don't need to actually understand how the organ works in order to restore its function. All we need to do is understand what it's made of, and more specifically we need to understand how what it's made of changes throughout life, so that we can reverse those changes, repair those changes, and put the structure and composition of the organ back to how it was at an earlier stage in early adulthood, and thereby restore its function, irrespective of our ignorance about how that function actually arises from that structure. That's just as true for the brain as it is for any other organ. So in the case of, one example of this is the fact that brain cells, neurons, don't divide. And in most cases, they don't have precursor cells that divide either. There are just a couple of areas of the brain that do exhibit the creation of new neurons throughout adulthood. The rest of the brain doesn't. Luckily, most of the rest of the brain also exhibits a very, very, very slow rate of cell death, so it's not really a problem. And the problems that we need to fix are the problems of accumulation of garbage inside neurons, for example, or outside neurons, that make those neurons not work so well even though they are still alive.